Hi, everybody. As Natalie, Ingrid already I will try to explain how we developed this new parvovirus vaccine that we have been working on since many years in BI. But first of all, I would like to shoot a question to you. So I really want to know what is your impression when I tell you, are you worried about parvo? What do you think about this virus? Do you have any comment on that? Do you want to share anything? Well, I just tell you what we got from the practitioners in the field, that some of them, they say that it's an old vaccine, an old disease, that there's nothing to really worry about, that everything is under control on the farm so far, and the wide use of vaccination can control the disease. Well, parvovirus, it's a well-known virus that is involved together with PRRS and PCV2 as the most common important pathogens involved in reproductive disease. So there's many publications that states that. And there's a recent publication from 2016 from a group in the northern Italy that they collected some aborted fetus from the field, and they determined what was the infectious cause. And parvo, as you can see here, it's among the 3 most prevalent detected virus that was present in those aborted fetuses. I really like this picture on this tree. That to me it really self-explanatory. So on the lower bar there's the year of isolation, and you can really see that the parvovirus is evolving. There's a higher genetic variability that was previously thought. The fact that we have really low number of different strains in those years could be that they really didn't check into that, but that's a real fact, that between the 3rd century there has been a genetic variability in the strains. So parvovirus was first isolated in 1965 in Munich as a contaminant of a continuous cell line used for the propagation of classical swine fever virus, and it was it took a while to really link the virus to the reproductive picture that we saw in the field. I will not enter into that because all previous speakers has discussed. Has a worldwide distribution, and it's present in all of pig herds, I would say. As Tania presented, there's novel parvovirus identified that the relation with the pig health has not really well determined yet. And together with PCV2, it's able to increase the clinical picture of the PCV2 infection. The virus has 2 non-structural open reading frames. So one encodes for the NSA1 and NSA2, which are responsible for the replication of the virus. And there's one structural open reading frame that encodes for the BP2 protein, which is an capsid protein that provides the antigenic differences, which determine this new cluster of viruses. And the BP2, which is the main target of the neutralizing antibodies. That's important to have that in mind, because this is the basic antigen that our vaccine contains. Again, the same dendrogram. So the thing is that, as Tania presented before, there's this 27A strain that was isolated in 2001 in Germany that has shown to have high pathogenesis and also high replication rate. And this is the one that we choose for our vaccine. It's important to know that parvovirus vaccines that are currently on the market, most of them are based on really old strains. The last marketing vaccine that I can recall, it's the IPRA one that contains this NADL2 strain, which was isolated in the 70s. So there has not been much improvement and much innovation in this pathogen since many years ago. So this strain was isolated in Germany, as Tanya said before, during an outbreak. It's a highly pathogen strain that in these cross-neutralization studies, they show that they really neutralize the old parvovirus that they used in the test, and that has a broad antigenic spectrum suitable for immunization against parvophile strains, the older and the current one. How we manufacture this vaccine. So I just want to tell you that I'm a clinician. I'm not an expert in production, but I will try to better explain you what's the basics of that. So as I told, the vaccine contains the 27A strain. Basically, we took that BP2 gen and we put it into a plasmid that was transfected together with the baculovirus, which is a virus that is able to infect insect cells, into an insect cells culture. And then the plasmid is absorbed by the virus, and then we have the master seed that effectively provides us with the BP2 antigen. The same platform is used for another really well-known vaccine from all of you, I guess, that is Circoflex, and the same basics. So the BP2 produced in this baculovirus expressing system is able to ensemble as virus-like particle structure, meaning that it has a 3D form, three-dimensional form that mimics the morphology of the virus. So it's basically, just roughly speaking, it's kind of the virus itself without the DNA material. That's shown that with the same amount of antigen has a really stronger immunogenic reaction compared to the administration of the whole inactivated virus. Again, the production process. So the expression is, as I told before, in a baculovirus system, we have the BP2 particles ensembled as virus-like particles. After this expression process, we have the purification step, which we give away or take away the proteins and cell debris and leaving only the BLPs. After this purification step, we just go through another purification step to have a cleaner output to get rid of all the residual cell media. It's called the Diatec process. And what we get is a really poor BLP component that then it's mixed with the implant flex, which is the adjuvant that's present also in Macoflex and Circoflex, which enables the prolonged release of the BLPs, and it's presented to the immune system in a slower phases. This process of the Diatec filtration, that's important because we get rid of any of the biocidal effect that can have the manufacturing process, and that enables us to mix our vaccine with a live vaccine such as ReproSig PRS EU. Just briefly explain you how we develop a vaccine. So as you can imagine, it's not an easy game. So it takes several years to bring one product to the market, so to step from here to here. In our case, it took around 8 years since the first idea of having a parvo vaccine until now that it's currently authorized. During this long process, we have to face a lot of things. So not only the efficacy or safety itself that it's tested in animals, but also the master seed, potency assays, the scale up, the production. There's a lot of things that we have to take into consideration. But what we do in the clinical department basically is to take care of the safety and efficacy studies, meaning that we test the product, the candidates in a different phases in animals to really generate data that it's able to be presented to the authorities and assessed and to get final the authorization. In this case, we also faced more inconveniences because the product was intended to be registered in Europe, in China, and the US. That means that three different regulatory bodies are assessing the dossier, meaning that we have a lot of different requirements that we have to comply, which makes things complicated. And another handicap that we had is that our marketing department asked us to provide a product that was able to be mixed with the reproductive PRRS EU, meaning that we had to double the number of studies to guarantee that this mixture was safety and efficacy against the PRRS. So briefly, what we have to demonstrate from the clinical perspective is that the vaccine is safe. For that, we have to use a high titer vaccine, and we have to perform lab studies and field studies. In Reprosect Parvoflex, we intended to register, well, we have registered the vaccine to be used under gestation and lactation. So that was, we had to test as well the safety in those two categories of animals. And on the other hand, we have to demonstrate that the vaccine is efficacious, meaning that, we have to run lab studies and field studies determining the onset of immunity, the duration of immunity, what's the minimum immunizing dose. And also, in this case, as I told before, we had to make sure that the mixture of the two products didn't harm one vaccine to the other one, meaning that after mixture, the vaccine is still efficacious against parvo, but also against PRRS. That ended up with all these studies. Some of them were easier than others, but I can tell you that the longest study in the history of our site is this one, which is a duration of immunity study that lasted more. We had the animals in our facilities for more than 1 year. Pregnant sows, it's even more complicated. Briefly, I want to share with you the animal model that we use for the efficacy study. So the animal model is really specified in the European Pharmacopoeia. So there is a guide what you have to do to demonstrate the efficacy. And the challenge model is that you have to challenge the animals at 40 days of gestation. We used a challenge strain from a clinical case isolated in Europe recently. We administered the challenge via intranasal dose and as well as intramuscular dose in 40 days pregnant sows. That's determined like this because you know that after day 35, the ossification and the organogenesis of the fetuses has already started, and we will guarantee that administering the challenge at 40 days of gestation, we will have mummies. That's what we assessed mainly. At 90 days of gestation, we kill the sows and we remove the entire fetuses. We start sampling always from the left horn to the right horn, identifying the clinical aspect of the fetuses, meaning if there were mummies, autolyzed, or normal fetuses. We measure the crown to rump length to know exactly when that piglet was dead. And then we took samples. So we did a pivotal PRRS study to check what were the best samples that we could take to be able to encounter the parvo in the fetuses, and we decided that kidney, lung, thoracic wash, and umbilical cord could be good samples. We ran PCR on all those samples, and if at least it was positive in one of these tissues, we consider the fetus infected. This picture just to summarize all safety studies. So it's as a general conclusion, the vaccine is safe to be administered during gestation, lactation, and also in non-pregnant gills. Here is just general view of a field study that was run in Spain with enrolling more than 800 animals, gills and multiporous sows, which we compare the safety of the safety and efficacy of our vaccine together with one competitor vaccine and the mixture of the parvo with the PRRS. And we saw that there were no difference between treatments regarding the local injection site reactions, rectal temperature, and return to estrus nor abortions. So as you can see, the maximum rectal temperature increase after vaccination is really low. The maximum is below 0.4 degrees. You saw that we did a lot of efficacy studies. I will only present one that was the most complicated one because it's the one that lasted more than 1 year, in which we wanted to determine the duration of immunity of our vaccine. For that, we split the animals in 2 different phases. Animals enrolled in phase 1 were the ones used to demonstrate the duration of immunity after primo vaccination, meaning that animals that had not been previously immunized with the vaccine, meaning that they need 2 doses before mating. So the animals were vaccinated at day 0, day 21. They were inseminated. They were challenged at 40 days of gestation, and they were killed at 90 days of gestation. And parallelly, we had another group in which we wanted to demonstrate the duration of immunity after the boost dose, after the animals were previously immunized at the same time point as the animals on phase 1, but at the time point where the animals of phase 1 received the challenge, these ones were boosted. And then the same animal model was implemented, meaning that the animals were inseminated, were challenged at 40 days of gestation, and they were necropsied at 90 days of gestation. Okay, that's a visual way to present the results, meaning that in each one of the rows there's one sow, and each one of the columns is one fetus. So the clinical aspect of the viruses is the green squares are normal fetuses, the red ones are mummified, and the orange ones are autolytic. So you can see here that, oh, sorry. I don't know. So the control group, as you can see here, were only 20% of the animals that were normal. The mean number of fetuses was slightly lower than the ones that received the vaccination, either combined with PRRS or with parvo. That might indicate that some of the fetuses were reabsorbed. So because we saw this same result in some studies. And so the picture is really clear. So here that 93.4% of the combined group were normal, whereas in the parvo mono group, we had 97.2% of the fetus were normal. We didn't stop here because we had the authorities, of course, want us to demonstrate what was the infectious rate of these fetuses, and we ran PCRs on those tissue samples that I presented before. And we end up with the challenge worked pretty well. 96.4% of the fetuses were positive, whereas all fetuses from the vaccinated groups were negative, meaning that we had 100% of protection in all litters. So the macroscopic aspect that we saw that there were some mummies or abnormal fetus in the vaccinated group were not linked to any of the parvo infections. Some results regarding serology. So we took samples during the whole study. This is the results from phase 1. So the animals were vaccinated at day 0, day 21. They started the seroconversion at day 28. All animals of the 2 vaccinated groups were positive, whereas in the control group, the animals remained negative until challenge, with what was here. And as Tania said before, viremia was at higher level at 7 days post-challenge, and there were some still positive animals, 28 days later, but I think that it was only one animal. So the viremia is really, really short. But 100% of the control animals showed viremia, and none of the animals vaccinated showed any viremia after challenge. We did the same with these phase 2 animals, which were boosted at day 202. And the picture that we had here is more or less the same that we saw before. In the control group here, we had only 7% of normal fetuses. Again, the mean number of fetuses was lower than in the vaccinated group, and 97.2% of the animals vaccinated were from normal aspect. And again, in this case, we even demonstrate that the challenge was fulminant. So we had 100% of the fetuses were parvopositive, whereas again, the animals that were vaccinated showed 100% of protection. And more or less the same picture on serology here. The animals at day 28, they were already seroconverted. At challenge, the animals on negative of the control group are still negative, and viremia again was present in all animals. Here, the viremia was a bit longer, but only in the control group, meaning that none of the vaccinated animals showed viremia after challenge. So as a conclusion, we can say that 100% of the fetuses from the both vaccinated groups were protected against infection. A reduction in the number of abnormal fetuses, either mummified or autolyzed fetuses in both vaccinated groups was observed in both phases of the study. Seroconversion was observed 28 days post-vaccination, and viremia was fully prevented in all vaccinated animals. So yeah, just to close out my presentation, a picture of all people involved in this project, which, as you can see, that's a multi-ethnic team. And I'm open for questions if you have them.